So to study sustainability of groundwater, I need to define the geometry of groundwater bodies and also how water moves, because replenishment takes place in through movement of water. Okay, now let me turn into the actual lecture after this introduction, after an introduction during which I clarified the importance of groundwater and groundwater assessment. This is really extremely topical. Now let me move to the lecture, and let me start. Let me see if I have already. Yeah, here I have our page. And let's click again on deductive methods, because groundwater is studied after surface water. So let me go down. Let me pass the part of IMOD. And here we are at, just 1 second, here is still IMOD, groundwater models. Okay. And I think that the best way to introduce this lecture is to use the Blackboard. Oops, sorry, I didn't share the screen. Or did I? Let me see. No, I didn't share the screen. So let me check here. Okay, here is groundwater models, and this is the page. Sorry, this is the page assessing water resources availability deductive methods. I go down, and I get here groundwater models. Perfect. I think the best way to introduce this topic is not to look at the web page, but rather to refer to use the Blackboard. So let me share this screen. You can keep it in front of you if you wish, and let me share with you my Blackboard. Okay. Okay, here we are. Just 1 second. I wanna open also the phone because I wanna check that you can see what I do. 1 second. Okay. Okay, let me see if I can see the Blackboard on the phone, which would be okay. Let me check. Do you see my white Blackboard on your screen?
Yes, we do.
Okay, thank you very much. Because with the phone I don't see it, but I know that the visualization of the phone is a bit more, it's a bit different. Okay, so let's refer to an aquifer, and let's refer to a portion of it, okay? And let me draw a cube. So let me do like this, okay? And let me see. Let me draw a cube. I think I have to change the dimension, okay? Let me draw a cube of aquifer, and this is red, okay? This is aquifer, and let me draw it in this way. Okay, and now let me draw the third dimension like this. Let me see. Okay. And then in this way. Perfect. This is, let's suppose that this is a cube of aquifer, and let me just adjust it by deleting here. This is okay. And let me just see if I can put it in the center. Very good. Okay, let's suppose that this is a cube of aquifer, And what is this cube actually? We can say that it's our control volume. So what is a control volume? It is a portion of the aquifer with respect to which we study the movement of water. So we want to study the dynamics of this portion of the aquifer. And we call it, this portion of the aquifer, we call it control volume. But now let me give you a formal definition of the control volume, because this is something that it's a concept that is frequently encountered in engineering. It's the control volume in rigorous terms is defined as a mathematical abstractions, which is very often used in mechanics, and it is a portion of space. So it's a volume contained into the space, which can be fixed or can be moving, but without, if it moves, it's without acceleration. So we say that it's this control volume is located into an inertial frame of reference. So remember, the control volume is a portion of space which can be fixed or can move without acceleration, and through this volume, we have a continuum that is flowing. And in our case, this continuum is water. So in our case, the control volume, again, it's a portion of space through which water can flow. And this portion of space can be fixed or moving. Okay, if it moves, we say that we are operating into a Lagrangian frame of reference. If it doesn't move, we say that the control volume is fixed. So when we dealt with catchments, surface hydrology, rainfall runoff models, our control volume was the catchment, and it is, of course, fixed. When we refer to rivers, sometimes we study how water flows into rivers. Our control volume is a river reach, and it's fixed. In the case of the aquifers, the control volume is a portion of the aquifer, and it's fixed. Okay, so usually in the study of aquifers, our control volume is fixed. Now, the control volume, our control volume is the cube that you see on the screen, okay? And let me give to this cube dimensions in order to be clear. And so let me just, now I write by hands because it's easier for me. And just 1 second, because I still have, okay, now I have the, so this dimension here, it's, this dimension here is dy. I'm using the same symbols that you can see on the figure that is on the web page. This is dz, and this is the x, okay? So let's suppose that we have water flow and passing through this volume, and let's suppose that the water flow has 3 dimensions. So water is flowing in the x direction, and we call the flow per unit area with the symbol lowercase qx. This is the flow per unit area in the x direction. And then we have q here, qy. Oops, sorry, because it's lowercase, not uppercase. Qy. And then we have here qz. Okay, now how can we study the movement of water through this control volume? The principles are the same that we used for surface water, and the principles are conservation of mass, conservation of energy. So, I mean, the principles are the same, but of course, the control volume is different. And then we have to write these conservations in a different way. And first, let me start from the assumptions. The assumptions are that the fluid is incompressible. These are the first two assumptions that I make. So water is incompressible, which means that the mass density of water, let's call it rho W, is constant. And the second assumption is that there are no sources of water mass in the control volume. So we have water flowing in and out from the control volume, but we don't have sources of water. And this is another assumption that we make. Okay, very good. Now, if we call with the storage into the volume with the symbol W, which depends on what? Depends on the three spatial coordinates of this volume and depends on time. So, of course, the storage into this control volume depends on the coordinates depends on three representative coordinates x, y, and z of the control volume, and depends on time. Okay, and then let's denote with the symbols Q in. Let me use. Okay, this is. Sorry. Q in. Q in is the inflow into the control volume, which again depends on the three spatial coordinates and time. And let's call with the Q out the total flow out from the control volume. Again, this depends on X, Y, Z, and time. Okay, very good. Now, let me write the mass balance equation. Let me change the color of the writing because here we start our mathematical development. So let me write the mass balance equation, and then it is very simple to write it. We can write that the partial derivative of W, X, Y, Z time with respect to time, it's equal to Q in X, Y, Z time minus Q out X, Y, Z time. Okay, this is very simple. So this is equivalent to what we did, for instance, for the linear reservoir. Okay, and now we have to develop this equation. So to develop this equation, let me I think it's better if I open another sheet because I could also move. Let me check if I have some space in the same sheet. Okay, I can develop it here. Okay, so I'm moving on the left. And then if you want to keep the figure this in front of you, it's very simple. You have to go to the web page. There is the same identical figure. Okay, and you can follow there my development. Okay, very good. Now let me develop this blue equation that I wrote here in the part of the blackboard that is now on the bottom right. Okay, let me develop it. And let me start by saying that Q in can be decomposed into three components. So the total flow, capital Q, entering into the control volume can be decomposed into three components along the three axes. Okay, so I can say that Q in, I can write it in this way: Q in X, Y, Z, T is given by the flow Q as lowercase qx, which again depends on the three coordinates. On the four coordinates, three coordinates x, y, z, and time. So Q depends on four coordinates. Let me drop them for the sake of simplicity, okay? So what is lowercase qx? As I said, it's the specific flow of water in the x direction. Specific means flow per unit area. So to get the total flow, I have to multiply by the area of the surface that I'm considering. So the y, the z, okay? So lowercase qx times the y, the z, it's the flow in the x direction. Okay, now let me sum the flow in the y direction plus qy, and this is to be multiplied by the x, the z, plus now I have to add qz, and this is to be multiplied the x, the y. I hope it's clear. Okay, this is q in. Okay, and now what about q out? Q out. Let me write the coordinates here, and then I will drop them, okay? In the right-hand side of the equation, like I did for the previous equation, which is placed above, I will drop the coordinates for the sake of simplicity. Okay, so Q out, we can write it in this way. Let's consider the three directions again. So let's now refer to the x direction. So Q out is equal to Qx, which is the flow entering. Okay, it's the specific flow entering. And now I have to write to this because I'm referring now to the exit surface. Qx is the flow entering, but I have to refer to the exit surface. So let me add the partial derivative of Qx with respect to x. And this is my flow out, okay? So it's given by flow in plus the partial derivative of the flow along the same direction. And this is to be multiplied by the x, of course, okay? And now I have to multiply it by the surface, the y, the z. And then I have to add the other two components. So plus qy plus the partial derivative of qy with respect to the y direction, the y, the x, the z, plus I have the third component. The third component is here, qz plus partial derivative of qz with respect to z in the z, the x, the y. Okay? It's a bit cumbersome, but not difficult. Okay, so now I can substitute these two expressions. So let me change the color. I can bring this one here and this one here. Okay, very good. Now let's make the substitution. And it's just a substitution. I'm not developing anything. I can write then partial derivative of W with respect to time. I'm dropping the dependence on the four coordinates for the sake of simplicity, because otherwise it becomes really heavy, okay? But in the web pages, you will find everything there, okay? So now let me write that the partial derivative of W with respect to time is given by Q in minus Q out. So let me write Qx, I'm just rewriting the y, dz plus qy dx dz plus qz dx dy minus, and then there is q out. I write it below here. qx, sorry, plus partial derivative of qx with respect to x in the x, dy dz, and I write also the other two just for the sake of clarity. So qy plus partial derivative of qy with respect to y in the y, the x, the z. It's not a plus, but it's a minus. Sorry, because I had a minus in the original equation on the right. I had a minus, so it's minus here. Sorry, minus here, and then there is a minus again here for the third component. And given that I go to a new line, the minus I have to put here a plus, okay? Because minus is already in the line above. And so I can write qz plus partial derivative of qz with respect to z in the z, the x, the y. Okay, very good. This is my substitution. And I think everything is okay. And now, let me just note that here I can eliminate some terms, because you see this one, I can eliminate it with this one below, because there is a minus sign, and therefore I can eliminate it, okay? And the same thing for this, and same thing for this and this, okay? So I can rewrite the equation in this way. Partial derivative of w with respect to time is equal to minus partial derivative of qx with respect to x in the x, dy dz, minus partial derivative of qy with respect to y in the y. It's not necessary that I put these parentheses, so let me just cancel them. When we can simplify the mathematical notation, let's simplify it. Okay, very good. And then I can write minus partial derivative of qz with respect to z, the z, the x, the y. Okay, so we got to a simplified form. And here I see that I forgot here, I'm sorry, in the second term, I forgot the x, the z. So I added it there. Sorry for that, I hope it's clear. But in order to remember this equation, just remember that each term in the right-hand side is multiplied by the x, the y, the z. Okay, and then we have the three partial derivative of each flow component with respect to the three direction of space. We can write it in this way if you wish. Derivative of w with respect to time is equal to minus partial derivative of qx with respect to x plus partial derivative of qy with respect to y plus partial derivative of qz with respect to z in the x, the y, the z. Okay, this is a compact form to write this equation. Okay, so far so good. Now we have to introduce a definition. So let's just keep this equation in mind, and let me simplify this blackboard in this way. Let me take this equation. Let me take this equation here. Okay, let me copy it and let me paste it as a new level. Okay, good. And let me bring, now let me delete the part here which I already developed. So let me delete this. Good. And let me now bring this equation up. Very good. And let me delete this. Oops, sorry. Let me delete this. Okay, perfect. Very good. Now, let me introduce a definition, and the definition I want to introduce is that of volumetric specific storage. Before I introduce this definition, let me recall you what we are doing, because we have to keep a clear idea of our frame of reference. We want to study the movement of water in an aquifer. And to do that, we have to write a mass balance equation, which is the one that we are writing now. Okay. And then later on, we will need to write a energy balance equation. But now, for now, let me just refer to the mass balance equation. I repeat what we are doing. We need to study the movement of water. Why? Because we want to know whether if we take water from an aquifer, this is sustainable or not. So we assume that when we take water from an aquifer, water moves and replenishes what I have taken. But in order to get a confirmation of this, we need to study the aquifer, okay? Otherwise, we cannot get any idea of sustainability. Okay, and then we are writing the mass balance equation for a portion of the aquifer. Of course, you can extend this portion, this control volume, to the whole aquifer, but now let's refer to a very simple part of it, okay? And why we need to refer to a very small part of it? Because the aquifer is heterogeneous. So if I referred to the whole aquifer, you know, the flow is changing in this whole aquifer. I cannot take only one value of flow. I cannot take only one value of velocity of water, of replenishment, because the aquifer is heterogeneous. And therefore, the trick is that I refer to a small portion of it. So the control volume is very small. Okay, this is something that I didn't say at the beginning. This the x, the y, the z, implicitly, I named these coordinates, these sizes, these dimensions, I named it the x, the y, the z. Implicitly, I meant to say they are very small. But now I'm giving to you the explanation why these need to be very small, because the aquifer is heterogeneous. Okay, in the catchment, we assume that the catchment was a whole unique. In the aquifer, we cannot do that, okay, because you know it's too heterogeneous. Okay, very good. So we are now writing the mass balance equation for this very small piece of aquifer, and I have got the expression that you see on the top left of the screen in blue. Okay, perfect. Now I need to work on the left-hand side of that equation. Because, you know, I have several unknowns in this equation. One unknown is the flow. So the three components, lowercase qx, qy, qz are unknowns. I already worked with them a little bit. Now I have a second unknown, which is w, which is placed in the left-hand side of the equation. I need to work on it. Okay, I have to find an expression for it. Okay, so let me then introduce this definition, which I put in red, volumetric specific storage, which you can also simply call specific storage. And what is the specific storage? It is defined as the volume of water that an aquifer releases from storage. I will repeat later on. It is defined, because the definition is not finished, it is defined as the volume of water that an aquifer releases from storage per volume of aquifer, overall volume of aquifer, per unit decline in hydraulic head. Okay, so let me just make a sketch to clarify what I'm saying. And then I will delete this sketch. Let's suppose that we have an aquifer, and let me depict it, okay? And for instance, let me say that this is the ground, okay? And beneath the ground, so here I have my trees, etc., my houses, whatever. And beneath this ground, we have a confined aquifer. Let's suppose that it's confined. I can make the same reasoning for an unconfined aquifer, but let's say that the aquifer now is confined. So this is my aquifer, okay? I have water into it. Now, if I dig a well in this aquifer, and let's suppose that this is my well, okay? This is my well. What happens? Given that the aquifer is confined, water comes up along the well to a certain level, okay? Good. Now, the level may be whatever. It may also happen that the level is such that water springs out from the well. In this case, we call it an artesian well. Usually, it's not the case. Usually, we are not so lucky. Usually, the level in the well is beneath the ground. So let's forget about the artesian well, okay? Now, of course, an important indicator of the state of the aquifer is the water level into the well. And we say that this water level into the well, we call it hydraulic head. We have to refer it to a reference horizontal plane. Let's suppose that this reference horizontal plane is the lower level of the confined aquifer. Of course, you can select whatever horizontal plane you wish. So let's suppose that the aquifer has the lower level that is horizontal, and we can take it. And then we say that this is the hydraulic head. The level of water into the head with respect to an horizontal plane is the hydraulic head, okay? Let me just, write here, hydraulic head. I am keeping an eye to the watch because we have 5 minutes. Okay, this is the hydraulic head, fine. And keep in mind that the hydraulic head is a synonym of the energy of the aquifer, of course, because of course it's potential energy. If the water can come up along the well, it means that it has energy to come up and to climb up, and therefore it's a synonym of the energy, and it's also a synonym, the hydraulic head, of the pressure, okay, of the pressure of water into the aquifer. Of course, because the higher the head, the higher the pressure that this water makes on the aquifer. Okay, So what is the volumetric specific storage? It's release. I write now it, okay, in order to make it clear. Release from storage, it's abbreviated, this writing. Release from storage per unit volume of aquifer and unit decrease of hydraulic head and unit of hydraulic head. So what is the unit of this volumetric specific storage? The unit, let's call it with V. No, let's say it's not V actually. In my, sorry, one second. In my web pages, I called it SS. The unit of SS is 1 over length, okay? 1 over length. So what happens when I take water from a well? Typically, the hydraulic head goes down. And then I can estimate the volumetric specific storage as the water that I took from the well, the volume of water that I took from the well, per unit volume of the aquifer and unit decrease of the hydraulic head. So it is quite simple if you define it in this way. On the other hand, you understand that this is a relevant property of the aquifer, which is related to sustainability of the use of water. Because it's clear that if you take a lot of water from the aquifer, a lot of it, and you don't see a significant decrease of hydraulic head, it means that your aquifer is sustainable. Your water withdrawal is sustainable. Conversely, if you take a tiny volume of water from the well and the level in the well goes down a lot, this means that this withdrawal is not sustainable. So the specific storage, which translates this relationship between the volume of water that you take and the decrease of hydraulic head, this is an indicator of sustainability. So this property of the aquifer, it's extremely important for sustainability, and you already understand that it's not easy to estimate it, because if I could easily estimate this volumetric specific storage, then it would be easy to give an answer to sustainability. Given that my premise was it's not easy to answer to this question, sustainability of groundwater withdrawal, then you understand that the volumetric specific storage, it's a relevant property which is not easy to estimate, okay? And there is a box in my web page. Let me now, because it's already time that we go to the conclusion for today. So let me share the Blackboard, and let me share the web page for a second, okay? There is a box in my web page here. I go down. This box, volumetric specific storage and uncertainty. Have a read at it. Because we got here, I go up, we got here with our computation, volumetric specific storage, we got here with our development of this mass balance equation, we got at this level. Actually, we already got, I think, to somewhere here. But okay, let's say that we got here. And then we will move forward next Monday with the subsequent development. The subsequent development of the mass balance equation, and then subsequent introduction of the energy balance equation. The two combined together will lead us to the final resulting equation that allows us to study the movement of groundwater. And if you read just this box it's useful. Volumetric specific storage and uncertainty. Okay. The remaining treatment that we have to do is not very long, so it's just a little bit, let's say, heavy, but in terms of symbols, etc. And you can see that in the web page, I kept the dependence on the 4 coordinates, which means that it looks heavier. Actually, it's not very complicated. And that's it for now. Do you have any question related to what we just discussed? Okay, I think I can stop my recording. I am very grateful to you that you always remind me to